I did it before I did this method. I did only phasers, so the order in which the questions are asked are based upon using phasers to find it. If you do it without phasers, then, well, if you notice, we sort of did this in the reverse order that we did. We found this information with this technique sort of in the reverse order from this, sort of. All right, about to put a stake in the coffin of AC. Any questions before we exploit Maxwell's accomplishments?
Why was Z sub L equal to X sub L times J, and then Z sub C was equal to X sub C, negative X sub C times J?
All right. So on that one, I could go with the trusting the math people a bit and say, you know, it works, but perhaps a little bit better rationale. If I look at just the capacitance circuit, I have some sort of impedance here. So voltage coming out of the power supply would be equal to the current for the power supply times the impedance. The current for the power supply is therefore equal to the voltage of the power supply over the impedance. We could similarly, we did it from this point of view, but the capacitor is going to be the same thing. So I of the capacitor is going to be equal to V of the capacitor over X sub C. And I'll put a little bit of a fancy flair to the X just to indicate we're talking about a complex number here, or complex function. I know that voltage, that for the capacitor, the current leads the voltage. So whatever the voltage is, so let's just, for the sake of this, let's assume the voltage has a phase shift of 0. So this is going to be some number times 0 over some number. Since the current leads the voltage, I know that my answer here is going to be some value times pi over 2. It's got to be 90 pi over 2 radians more than whatever that phase is. So from that, X sub C would be epsilon sub naught 0 over I sub naught pi over 2. When I do that division, I get epsilon naught over I sub naught times the angle negative pi over 2. That is just X sub C. And that negative pi over 2 is negative J. That's the rationale for making the capacitance a negative. The impedance, or whatever it's supposed to be called, for the capacitance, negative. Does that answer the question?
Yeah.
That was not a convincing yeah.
It doesn't know.
Pardon?
It doesn't know.
Okay. I'll settle for that for now until I get some great insight in the middle of the night. Then I'll call you.
Can you go back to page 3?
Oh, yep. I'm sure there's a faster way. assuming this is still running. Oop. Here, I'm getting low on juice here. So again, Coulomb's law. So up through up through test 1A and 1B, it was only Coulomb's law. That was the only physics equation we had. We get into magnetism and the fact that monopoles do not exist that we have found. And so, oops, forgot to put in the differential there. Then if we look at the magnetic flux through any three-dimensional surface, that's going to be equal to 0. Because we have just as many lines going in as out. We have Ampere's law. So these are Gauss's law. Or Gauss law, depending on how you want to deal with it. Possessive of something ending in an S. So if I look at a loop, B dot dl, so we're not dealing with a three-dimensional surface, but basically think of a line that connects back to itself. That's going to be equal to mu naught times I. And then we have, so that's Ampere's law. And then we have Faraday-Lentz's law. That the line integral of the electric field around an enclosed surface is equal to the negative change in the magnetic flux with respect to time. So this is almost the complete set of what is now called Maxwell's equations, but Maxwell has made no contribution at all to these at the moment. All right. There does seem to be a parallel here. The fact that I've got the electric field times the area, magnetic field times the area, magnetic field times the line, electric field times the line. There are enough parallels that you might begin to suspect that are we missing something here? Well, the fact that there's no magnetic monopoles is the reason why that's not some sort of magnetic charge divided by mu sub naught. But I got a magnetic field here, but should I have an electric field here? That should say magnetic flux here. Should I have an electric flux there? So now let's enter Maxwell. Now let's bring in Maxwell. We've talked about the charge in equals charge out. This is one of Kirchhoff's rules. At the time, I suspect that I said there is an exception that I wasn't going to deal with at that point, but now let's deal with it. So any place along here with an exception is whatever current I have flowing in, I have flowing out. Nothing earth-shattering there. Primarily, we've exploited that when we've had a junction. Current flowing into a junction equals current flowing out. If this becomes positively charged, that becomes negatively charged. I have electrons piling up over here, an electron piles up on the right-hand side, an electron leaves the left-hand side. And you can sort of see that still seems to obey Kirchhoff's rules. However, if I look at the plates themselves, I have a charge, I have current flowing onto the plate, and the current flowing off the other plate. What happens in the middle? Is there something that we can deal with so that Kirchhoff's rule still works and that makes sense? All right, so I know that I'll have some charge on here, Q, and charge on here, negative Q. I know I have an electric field coming off of this. So if I look at that plate, I have an electric field going from the positive to negative. That is equal to Q over surface charge density divided by epsilon sub naught. Again, assuming free space. And so, all right, take a moment here because, get back to that. So I have my electric field times my area. Because if I think about that plate, if it's an ideal capacitor, the only place that there is an electric field is in between. There's no electric field over here, no electric field over here. It's just in between. So if I think about if I got a surface here, if I put a Gaussian surface around the positive plate, I have an electric field going through this area right here. My electric flux would be whatever that electric field is times that area. So that's going to be sigma over epsilon naught times my area. And sort of doing a circle here. That is Q over A over epsilon sub naught. A, which is just Q over epsilon sub naught. So no real big surprise there. If I think about the fact that I am putting a charge on the plate, moving one from the other plate, there's sort of this displacement going on, and so I know that current is dq dt. Q from, I guess, here, I have Q over A epsilon sub naught is equal to my electric field. Q is equal to A E epsilon naught. So dq dt becomes dAE epsilon naught dt. Epsilon sub naught's a constant, it would just factor it out, so I get epsilon sub naught dAE dt. So I've got an electric field times an area, which is
An electric flux.
so it's epsilon sub naught ddt of the electric flux. So if I think about that as a current, it's called the displacement current as opposed to actual current or charge current, however you want to word it. Traditional, I guess traditional current. Slightly different context. But if I now expand this to, I've got my traditional moving charge current plus my displacement current. I now have Ampere's law with Maxwell's addition, correction, supplement. And so I can write this as mu sub naught I, it's actually I enclosed, that with the current that's flowing through the loop, plus mu sub naught epsilon sub naught d phi E dt. And that was Maxwell's contribution to Maxwell's equations.
So why did they name all of them after him?
What he did with it was had a major impact, but it does seem, well, just what Maxwell did not name it after himself. So someone else did. I don't know who did it, but yeah, it does seem rather blowing up there. But what he did with it was significant enough. I guess they wanted to honor him with something. Questions before I talk about what you can do with this from a physics point of view? All right. If I have a charge here, Q, I have an electric, so it's just so it's positive for the sake of the drawing. I have my electric field coming off of it. If I'm sitting right here looking at it, I got an electric field line that's coming right through me. And now the charge charge moves over to here. And so the electric field going through me is now going in that direction. So just by moving the charge, the electric field changes that I'm experiencing. So charge moves, Q moves, causing a change in this electric field. Since I have a change in the electric field, I really have a change in an electric flux. If I have a change in the electric flux, that means that I've produced a magnetic field based upon this new bit right here. If this is not zero, that's not zero. So that produces a magnetic field. If I move the charge again, so that in this round, I will have a change in the change of the electric field, which causes a change in the change of the electric flux, which causes a change in the magnetic field. Well, if I change in the magnetic field, that means that I'm going to have a change in my magnetic flux. If I have a change in the magnetic flux, that means I'm going to create an electric field based on Faraday's law. If this isn't zero, that can't be zero. So if I oscillate this particle back and forth, I will have a change in the change in the change of the electric field, which causes a change in the change in the change of the electric flux, which causes a change in the change of the magnetic field, which causes a change in the change of the magnetic flux, which causes a change in the electric field, which then causes a change in the electric flux, which we get this cycle going. So this produces the idea of the self-propagating electromagnetic wave. What can we do with that? Well, we can figure out how fast that sucker's going. So let's figure out what is the speed of an electromagnetic wave, the self-propagating wave, where I've got this change in electric field, which causes a change in the magnetic field, which causes a change in the electric field, and so on. So first thing we need to do is figure out what's the generic equation of a wave. So I will start out with a question that has stumped students for quite a while. I will have P is equal to the cosine of Q. Just start out with that generically. If I plotted it, it would look something like that, at least one cycle of it, where that's my P axis and my Q axis. All right, here's the question that I hope doesn't stump you. What's the period of the wave?
Pi over 2, or pi. Pi.
Not pi.
2 pi.
Pardon?
2 pi.
2 pi, yeah, there we go. So period's 2 pi. Anyone want to stand up and go, Sarah, how could you think that? Or are you happy with 2 pi? Or suspicious about 2 pi? All right, the period equals 2 pi. What's the wavelength? Do it.
Is it not just 1?
How'd you get 1? You think of the amplitude?
I think.
Amplitude's 1, I'll buy that. Wavelength, I heard 2 pi. They put a big question mark next to both of them. Is the period 2 pi or the wavelength 2 pi? Or can you not know which one it is? what would tell us if it's the period that's 2 pi or the wavelength that's 2 pi? Suppose I gave you y equals 3 cosine of 2t. What's the period? All right, this is reaching back into the depths of your memory, I'm guessing.
It's not 4 pi.
Period is appropriate here. Pardon?
It's not 4 pi, is it?
It is not. You did the wrong thing with the 2.
Pi.
Pi. It's whatever's in front of time here, it's if that's omega t, the period is 2 pi over omega. If we think about that, period is 1 over the frequency, so that's 1 over the frequency. If you cross multiply, you end up with omega is equal to 2 pi times the frequency that we were actually using earlier today. Divided y is equal to 3 cosine of 2x, assuming traditional meaning of x. What's equal to pi? Yeah, the wavelength is. So whether the period is 2 pi or the wavelength is 2 pi, it depends upon what q is. Is q a time or is q a position? The point of this is that we need to take both into account when we have this traveling wave. So if I did a plot of position versus time, amplitude versus position, so we'll make that y